So, an advantage of taking a mathematical and data-centric view of the world is that it lets us describe very complex realities in very simple terms, although those simple terms are not always easy for a human to understand. So, a prime example is describing the world or the experiment that we're interested in as a high-dimensional matrix. Now, a typical system of arbitrary complexity can be represented as a 4D matrix, with each particle having three spatial coordinates at every time coordinate. Now, of course, a matrix like that might not be the most complete or compact means of describing a system. Uh, a space like that is not limited to four or any rational number of dimensions, and there might be better ways to compress the data, so to speak. But for ease of visualization, we can limit ourselves to four dimensions when we start to think with this cognitive tool, and it can be applied to very different parameters if that's what we want to do later. Now, let's take a concrete example, um, because we're talking about probability over time and how past probabilities affect future ones. So it's a difficult concept to get our minds around. So imagine a very simple example of a chess game. So if we have a chess game with n moves, we can represent those as an 8 by 8 by 8 matrix. So a three-dimensional space that describes each square on each turn. And depending on how we count duplicate pieces, uh, so all white pawns, for example, we could count those as individual pawns, or we could count those all as just a white pawn is on that square. So each of the 64 points in space that describe the game would then have between 15 and 33 possible values. Now, suppose we start with a simple 100 move game, and we're counting fungible pieces as only once. So we would say that square has a white pawn on it rather than that square has a white queen's pawn on it. So in that case, there'd be an upper bound of 8 times 100 times 15, so 96,000 possible spaces that describe the various 100 move chess games that are possible. Um, there'd actually be fewer than that, of course, because not all moves are legal. But even if we take the 96,000 possible spaces that describe the possible 100 move chess games, that's a large number, but it's not impossible to imagine. We can imagine walking through 960 stacks of games, and each one is comprised of 100 vertically arranged chessboards that show one possible progression from turn 0 to turn 100. So that sort of four-dimensional space with which we can describe an arbitrary physical system is very similar to this abstract idea of a complete chess game. So there are two significant differences. The first is that being four-dimensional, we can't use our spatial intelligence. So we can use our spatial intelligence when we imagine the possible chess games that could be played in 100 moves. We can't apply our spatial intelligence to imagine walking around a four-dimensional space the way we can a three-dimensional space. Mm. And that makes it harder for a human to understand it, but in an abstract way, it doesn't make the mathematics harder for a computer to crack. The other difference is a lot more significant, and that's that the pieces of a chess game have discrete, clearly identifiable locations. So particles in a 3D space aren't like that. They're properly represented by either rational numbers or confidence intervals. With the way we currently understand non-locality, it might be more accurate to think of the position of a particle as a normal distribution. And the more accurately we're measuring, the narrower, so you can have a flat normal distribution or a narrow normal distribution. More accurate measurement makes it a narrower normal distribution, but it never collapses to a point of certainty. And that adds an additional level of difficulty if we're trying to be rigorous. But we can still use our intuition, uh, which is informed by this idea of chess towers or any other kind of um, system with discrete states, a two-dimensional game board with discrete states stacked. We can use that same image to help us think about how things work in four-dimensional space or four-dimensional reality. Space is just three of those dimensions. So in that context, a holon model of time is pretty directly accessible. So if you consider the space describing a chess game, if you know the first and last position, and there's an arbitrary number of moves in between, we can deduce a small number of possible progressions that the system may have undergone between the initial and the end state. So some transitions are more likely than others. Um, the moves an opponent makes are always partially predictable, and reducing our opponent's options is an important part of a chess strategy. So this is a great image to keep in mind if we're modeling a more abstract idea of agency in space and time. So in chess, there's factors we control, factors we don't, desired outcomes, multiple paths to them. And it's a useful metaphor because being two-dimensional, we can imagine the progression through of time via a third dimension. And the 4D space is less easy to visualize, but keep in mind this image of an initial and an end state with the indeterminate in between states, because that's important to the whole idea of a holon, that is, where the initial and end states are accessible to the rest of the universe, but the interstitial period is not. Now, a person experiencing flow is essentially taking a low probability path through four-dimensional space. If the desired outcome has a high probability, then it's usually not a challenging enough navigation for flow state to arrive. There needs to be some challenge, which means there needs to be um, there needs to be some difficulty or some improbability of reaching the desired end state. Um, And obviously, probability at the scale of human agents is so complex and relies on so many non-random and non-random factors that we can't model this with hard data these days. But we can represent it in theory using a very simplified model. So if we consider a plane with a smoothly adjusted probability of finding a particle at every given point, we can imagine a matrix, uh, just a two-dimensional matrix now, and essentially showing a normal distribution of the point where the particle is likeliest to appear, and then a decreasing cloud of probabilities around that. And that kind of probability density is a standard tool for visualizing particles interacting. Now, if we replace our grid of squares with a grid of cubes, so if we turn that matrix from a two-dimensional matrix to a three-dimensional one, then we have a probability distribution in 3D space. And if we replace those cubes with tesseracts, then we're visualizing probability distributions through time. I make references to a holon in time, but that's the last time I'll mention tesseracts here because I have a hard time visualizing them, I have to admit. Now, most of the time, the path we take through this kind of four-dimensional space is comfortably broad. The same destination is accessible via various sequences, and the clusters of values are quite loose around one or more ideal paths. Um, so the number of possible paths when we're successfully navigating between a beginning and end state, the number of configurations encompassing the beginning and end states narrow the harder the thing we're trying to achieve becomes. So possible paths become more tightly constricted rather than having a very broad range around an ideal path. That ideal path becomes a sharper a narrower normal distribution. And what form that narrowing takes can depend to a significant degree on the kind of target end state we're working with. Now, think about the necessary prerequisites for flow to occur. Some of the most universally accepted precursors is intense mental focus in response to a challenging situation. So flow is thought to occur most reliably when a high degree of skill is applied to a high degree of challenge. And if we're approaching a mathematical description of this dynamic, we can represent a skill with the ability to navigate a particular sort of four-dimensional landscape, so to connect an initial state to a desired state via continuous intermediate states. And the more skilled we are, the more precisely we can navigate those intermediate states. Anyone can want a particular outcome. It's being able to chain the initial and the desired outcome together that defines a high degree of skill. So we could say then that a given skill challenge requires observing the right intermediate states between an initial and a desired condition. Or we could also say that it's necessary to avoid observing any intermediate state that rule out the desired end state. So if we're playing chess, we want to never observe our king in checkmate, because that prevents us putting the other side's king in checkmate. So if the skill challenge is easy, then the number of intermediate states that we can safely observe is relatively large. And as the skill challenge increases, the number of acceptable intermediate states decreases. And the response of someone pursuing excellence in the skill question is to narrow their focus. They put ever more energy into following the narrow path of intermediate states that connect the initial and desired conditions. Or we could also say, because of how flow works, that the current conditions and the desired conditions, because like we stated earlier, it is possible to have to adapt on the fly in flow, but it's still necessary to be focused enough on the next set of steps that bring us towards the desired conditions.